Welcome back. In this video, we are going to learn about the types of the internal loads that arise at the sectioning plane of the rod or any other solid rigid body. And then we will learn about the basic mechanism of the normal stress and finally determine the normal stress at the section SS of the rod as shown in the given figure of this question, which is from GATE 2013 ME Set A. Now, before we move on, let's first read out this question and analyze it. A rod of length L having uniform cross-sectional area A is subjected to a tensile load P as shown in the given figure. If the Young's modulus of the material varies linearly from E1 to E2 along the length of the rod, the normal stress developed at the section SS is. Alright, so what this question is actually asking is about the normal stress that develops at this section SS due to the application of the two tensile forces P at the opposite ends of this rod. Alright, so this question mainly asks to find the normal stress, or more precisely say the internal normal stress developed at the section SS. And to do that, we first need to find the internal normal force at this section of the rod, which we can do by considering either left or right portion of the rod from its SS section, and then reveal the internal loads at the SS section. Alright, so we can consider either left or right portion of this rod with respect to this SS section and reveal the internal loads that act on that section. Alright, so let's say we consider left portion of the rod on the left side of the SS section and draw its free body diagram FBD separately, and by doing so would cause the internal loads to be acted upon at the section SS on this left portion of the rod. Alright, so what does that mean is that when we consider the left portion of the rod and draw its FBD, internal loads would act on this left portion of the rod at this SS section, and By those internal loads act on the left portion of the rod at the SS section because we want them to act or we assume them to act to maintain the same condition of this left portion of the rod as it was before sectioning this rod. Alright, in other words, we consider those internal loads to act at this SS section of the left portion of the rod. So the condition of this left portion of the rod remains the same which was before sectioning of this rod at this SS section. Therefore, those loads that act at the SS section of the left portion of the rod maintain the same condition of this left portion of the rod which was before the sectioning of the rod at the SS plane. Alright, so that's how the internal loads arise after the sectioning of a rigid or a solid body. So let's draw the FBD of the left portion of the rod and and show the internal loads at the SS section. So there we have it, FBD of the left portion of the rod. As we can see here at the SS section that three loads seem to act, which are the internal loads at the SS section. First is the normal force. Let's say F, which always acts perpendicular to the plane surface or section SS in this case. Right. So the force F acts perpendicular to the section SS and becomes the normal force. Second is the shear force, let's say V, which always acts parallel to the plane surface or section SS in this case. And this shear force V acts parallel to the SS section. Alright, and that is why it becomes the shear force. Alright, because it acts parallel to the SS section. Alright, and the third is the moment. Let's say M, which acts either in clockwise or counterclockwise. We can assume any direction, alright, for two-dimensional problems such as this one. Alright, so this problem is two-dimensional. So in two-dimensional problems, uh, either clockwise or counterclockwise moment is considered. In this free body diagram, while there seems to be three loads acting on the SS plane, Actually, there are basically two loads. One is the internal force, whose perpendicular components are the shear force and the normal force, and second one is the moment. All right. So whenever we section a solid or a rigid body, there are always two types of internal loads arise. First one is the internal force, which resolves into shear force and normal force, and second load is the moment. All right, and the shear force and normal force remain perpendicular to each other, or kept perpendicular to each other for the shear stress and the normal stress evaluation purposes. If we were also to draw the FBD of the right portion of the rod, then the directions of those shear force and normal force and moment would be in the opposite direction of the shear force, normal force, and moment in this free body diagram. Right. So if we were to draw the free body diagram of the right portion of the rod, then the normal force would act on the SS plane in this direction. All right. So opposite of this force F, and the shear force would act on the SS plane of the right portion of the rod in the downward direction. All right, opposite of V, and the moment would act in the counterclockwise direction, that is opposite of M. All right. So when we combine both portions of the rod, then the net resultant of all the forces and moment would become zero. All right, because that's what the initial condition is before sectioning the rigid body or the rod in this case. Let's move to the next page. Since in this problem we only need the internal normal force F, we would ignore other internal loads and focus only on this internal normal force F and try to determine it. To find the internal normal force F, we would apply the first condition of the static equilibrium to the FBD that we have drawn of the left portion of the rod. Viewers might be wondering what the first condition of the static equilibrium is and why we need to apply it here. I would say this condition is about balancing the forces acting on a body, such as the left portion of the rod, in any particular direction. And the reason behind its application here is that since the rod initially was in static equilibrium because equal and opposite forces P acted on rod's ends, so when we consider left portion, of the rod for our analysis, that static equilibrium condition must still be maintained, as the internal normal force F acts in the rightward horizontal direction, as we can see here in our free body diagram, that F is acting in the rightward horizontal direction, as we assumed. We apply this first condition of static equilibrium, that is force balancing, to the FBD of the left portion of the rod in the horizontal direction to determine the internal normal force F by assuming rightward is the positive and leftward is the negative direction. Note, the force balancing in any direction is equivalent to setting the algebraic sum of the forces to 0 in that direction. So we set the algebraic sum of the forces in the rightward direction to 0, right? Meaning that in our free body diagram of the left portion of the rod, what we would do is we would set the net force on this left portion of the rod to 0 in the rightward direction, right? So first we would find the net force in the rightward direction, which would be equal to F minus P, alright, because we assume rightward is the positive direction and leftward is the negative direction. So when we find the net force in the rightward direction, it would be F minus P, right? And we would set it to 0. So algebraic sum of the forces in rightward direction is equal to 0. So we have the algebraic sum of the forces in the rightward direction on the left portion of the rod, alright, which is F minus P. We would rearrange it and find the force F. So we have the force F equal to P. Now before we move on and find the normal stress that acts at the SS section of the left portion of the rod, let's go back to the free body diagram and try to understand it, how that normal stress acts at the SS section. Alright, so when this internal force F, which is a normal force because it acts perpendicular to the section SS. Alright, so when this internal normal force F generates, right, in the rightward direction, this force F causes the internal fibers of the left portion of the rod to exert the same force F at the SS section, right, and that resistive force F that those internal fibers of the left portion of the rod exerts on the SS section induces the corresponding normal stress. Alright, inside this left portion of the rod which acts at the this SS section. Now let's go back to our second page and move forward. Now to find the normal stress acting at the section SS of the rod, we would use the basic definition of the normal stress, right? Which is force per unit area or the ratio of the force and area, alright, on which the force acts perpendicular to that force, alright. Generally, the stress is actually defined as force per unit area, alright. Now, when we consider normal stress, then we use normal force divided by the area on which that normal force acts, right, and apply it here accordingly. So we use this basic definition of the stress and apply it here to write that expression of the normal stress accordingly. So we have the expression of the normal stress sigma SS acting at the SS section is equal to ratio of normal force acting at SS section on the left portion of rod divided by cross-sectional area of left portion of rod at SS section, right? So what this ratio actually mean is that the normal force acts perpendicular to the SS section on the left portion of the rod divided by cross-sectional area of left portion of the rod at section SS. Alright. So the cross-sectional area is equal to A, which remains the same because the rod is of uniform cross-section, and the normal force acting at a SS section is F. Right. So we write our next expression as so sigma SS is equal to F divided by A. Alright, now we plug the value of F which is equal to P. Now finally we have the expression of the normal stress at SS section which is equal to P divided by A. Right. So let's see which option is correct. So P divided by is correct. So option A is correct.